Welcome to MRU E-Learning powered by Malla Reddy University. I am Mohammad Arshad, working as an assistant professor in Data Science Department, School of Engineering, Malla Reddy University, Hyderabad. So in this lecture, we are going to learn about feature selection and scaling. In feature selection, help us to reduce the number of features present in the datasets, whereas scaling ensures that the data is in a particular range so that it equally contribute in the training of machine learning model. So in this lecture, our main focus is on feature selection and scaling process. So before going to start with the feature selection and feature scaling, first we will see the pipeline of machine learning model. In building machine learning model, first we'll take the data from various sources. So we take the raw data, then we'll perform some pre-processing, basic pre-processing techniques such as data cleaning. In this step, generally we handle noisy data and missing values data, or the data that is inconsistent, we deal with that. And after that, we'll perform feature selections to select only best features or the features that are very important for our training. And next step is feature scaling. In this feature scaling, we convert the data in a particular range with the help of some feature scaling techniques such as min, max, normalization, standardizations, or robust scaling to convert the data in a similar fashion or similar magnitude so that all the features contribute equally during the training of machine learning model. And the last phase is building a model. Before going to start with our main content, first we'll see what is feature engineering and what is the role of feature selections. So feature engineering refers to the process of translating a dataset into features such that these features are able to represent the data more effectively and result in better learning performance. Basically, there are two major elements. The first one is feature transformations. In feature transformation, generally we perform two operations: feature constructions and feature extractions. So in this lecture, we are not going to discuss about these feature constructions and feature extraction. We more focus on feature selections or feature subset selections. Feature selections and feature extractions seems to be same, but it is different. In feature selection, generally we'll take the input features and we'll select some top 3 or 4 out of n features, and we'll eliminate some of the features, and with the help of these selected features we try to build machine learning model. Whereas in feature extractions, from the original input features, we'll try to create new features through linear combinations, and we'll create a subset of features that basically are used for training of machine learning model. So our main focus here is to learn what are the feature selections techniques and what are the important point we need to consider while performing the feature selections. So feature selection is a process of choosing only the most useful input features for a machine learning model. Basically, by selecting only good features helps improve the model performance and reduce the noise, and also it helps us to make result easier to understand. When the number of feature is less, we can easily understand the features. The next question is important question is why this feature selections, why feature selection required. So the feature selections helps removing the irrelevant and redundant features. With the help of feature selection techniques, we can remove irrelevant features or redundant features. And also, this feature selection speed up the model training. As we know, the fewer features, fewer features need very less training time, and the time taken to the training of machine learning model will decrease. And the third point is interpretability. It makes model simpler and easier to understand. And also, once we have only good features, it prevents the model from learning noises also. So the main objective of this lecture is to identify and retain only the most relevant features with the help of a feature selection technique, reduce dimensionality, and improve the model efficiency, accuracy, and generalizations. So let's discuss more about feature selections. Before going to dive into what is feature relevancy and feature redundancy, another important point here is curse of dimensionality. Because of curse of dimensionality, feature increases and it leads to the volume of space increases also, and the data becomes sparse. When the volume of space increases, the data also becomes sparse, and the distance between the point become almost equal, making cluster classification impossible to find out. So when the data are very much sparse in nature, we cannot or we easily classify the data points. And also when the number of features are increasing, we cannot visualize the features. For example, if we have three features, right? Three features, so we can easily see all the data points in 3 dimension. As the number of dimension increases, right, it is very hard to visualize the data also. So these are the some issues in the high dimensional data. So as the number of feature increases, the computational resources also require more. At the same time, the training time also require more. Okay, and as the number of dimension are very high, the model performances will degrade due to the noise. So our main objective is to reduce the input features or input variables by keeping only the most informative features. Coming to feature relevance. So why feature relevance matter in feature selection? So in supervised machine learning, each predictor variable is expected to contribute to decide the value of class label. That means if any variable is not contributing any kind of informations, that features or that variables are irrelevant. Okay, that is not relevant for our model building process. So if the information is very less, then the relevant feature, the feature is very weak relevant or weak features. So in such kind of a cases or scenario, we either convert the feature into some other form or we can drop the features. In unsupervised machine learning, we can evaluate the data instance based on different variables. Variable which has no significance in deciding similarity or dissimilarity data instance marked as irrelevant variable in the case of unsupervised machine learning. Any feature which is irrelevant is a candidate for rejections. That means when we perform the feature selections, if the features are not relevant, then simply we discard that features. Coming to measure of feature relevance, it is measured by amount of information contributed by a features. In supervised learning or unsupervised learning, we have some method. With the help of that method, we can calculate the measure of relevance, feature relevance. Okay, feature relevance or amount of information contributed by the features. So in machine learning, there are different kind of a feature relevance techniques. The first one is mutual information. This mutual information is a basically supervised learning technique. In this, we use this formula to calculate statistical dependence between two variables, where marginal entropy of class is represented by HC, marginal entropy of feature represented by H of F. With the help of this formula, we can calculate the mutual information. If the mutual information values are more, then we can keep that data in our input feature, then we can keep this data in our original data set. In unsupervised learning, we use information gain or entropy to find it out the feature relevance. With the help of Shannon's formula, we can calculate feature relevance. This is the formula. With the help of this formula, we can calculate feature relevance, and features are ranked in descending order of information gain, and by specifying some percentage, we can select the relevant feature. For example, if I want only top 10% of features to be selected for my training of the model, then we'll specify 10% here and we'll select only top 10% relevant features for our study or our training of the model. Next important concept is measure of feature redundancy. As we know, the data may be represent similar kind of information. For example, date of birth and age column represent similar kind of information. With the help of measure of feature redundancy, we can measure similar information provided on multiple features. So these are the some methods. With the help of that, we can measure the similarity of features. The first method is correlation based measures, distance based measures, and other coefficient based measures. So let us look one by one. The first one is correlation based measure. In correlation based measures, we'll test linear dependency between random variables, and these values are ranging in between -1 to +1, and this is the correlation coefficient formula, Pearson correlation coefficient formula. With the help of this, we can find it out the redundancy between two variables. Another method is distance based measures. So with the help of common distance measures, Euclidean distance, we can calculate feature redundancy with the help of distances. So this is the formula: d of f1 comma f2 is equal to under root of summation I is equal to 1 to n f1 I minus f2 I whole square. Basically here we are finding out the distance between these two data points, and based on that we'll find it out the measure. So here specifically we are finding out the distance between the feature 1 and feature 2. Consider this example. In this example, we have two features. The first feature F1 is aptitude. The second feature F2 is communications. As you can see in this data, the data points are already in a scale form. If the data points are not in scaled, then we need to perform the normalization. As the data are already in a particular range, and the values, the magnitude of F1 and F2 are not very much different, we can directly calculate the distance between feature 1 and feature 2. So as we have calculated the distance between feature and feature 2, and with the help of this Euclidean distance formula, we got 81.75. So this 81.75, the distance between these two features F1 and F2 is 81.75. That means The distance between features f1 and f2 is high, hence there is no redundancy in feature 1 and feature 2. So we can keep f1 feature as well as f2 features for building our machine learning model. Another technique is Jaccard index or coefficient. It is basically measures the similarity between two features where the values are in binary. Okay, so with the help of Jaccard index formula, J is equal to n11 divided by n01 plus n10 plus n11, where n11 is nothing but a number of cases where both the feature have value 1 and 1. So in this case we can see case 1 and case 2, we have values 1 in feature 1 as well as in feature 2. N01 means a case where the feature 1 has value 0 and feature 2 has value 1. So based on this information, we have already written the count type, and we'll substitute this count type in our formula to get a Jaccard index. Here dj represent dissimilarity between two features. Okay, Jaccard distance is equal to dj is equal to 1 minus j. J is our Jaccard index, where dj represent dissimilarity between two features. So as we have calculated here, n1 is equal to n11 is equal to 2, n01 is equal to 1, n10 is equal to 2. So put all these values in the equation. J is equal to 2 divided by 1 plus 2 plus 2, which is nothing but a 2 by 5, which is equal to 0.4. So Jaccard index value is 0.4 and the distance is 0.6. That means the Jaccard coefficient between binary feature f1 and f2 is 0.4, indicating moderate similarity, and Jaccard distance dj is 0.6, which show considerable dissimilarity. Here the 60% is dissimilarity. That means we can keep such kind of a features f1 and f2 both in our training data set. Another similarity measures is SMC. The difference between this and the previous technique is in this techniques we have N00. That means we'll consider a feature where feature 1 value also 0 and feature 2 also 0. So with the help of this SMC also we can find it out the coefficient matching between f1 and f2. So here the simple matching coefficient SMC between f1 and f2 is 0.625, indicating that 62% of the features values match exactly. That means we may not keep both the features, as the feature 1 and feature 2 has more similarity. Other similarity matrix is cosine similarity, where we can find it out the correlationship between the features. So this kind of techniques generally used when the problem is text classification problem. Okay. So this is the let us calculate cosine similarity of x and y, where the x values, the input features are 2, 4, 0, 0, 2, 1, 3, 0, 0, and y value is this one. So the very first thing is we'll find it out the value of mod x and mod y and substitute in this formula. Cosine x comma y is equal to x into y divided by mod of x into mod of y. So with the help of this formula, we find it out the cos value is equal to 0.729 and the angle is 43.2 degree. In this figure, you can clearly see the cosine similarity between vector x and y is approximately 0.729 and the angle is about 43.2. Even though their magnitude may differ, the vector shows the similarity between X and Y. This is a feature selection process. The feature selection process consists of 4 steps. The first step is to generate all the possible of subset. Okay, the first step is generation of possible subset. Next step is evaluation of subset. Then we'll keep on, right? We'll keep on searching the subset until we'll get the goodness of subset. Until we'll get our desired output. We'll take the subset of features, we'll evaluate, and if the features are good enough, then we can stop and we can validate our result. Basically, this feature selection process is an iterative process. These are the approaches. Feature selection approach. The first approach is filter approach. Second approach is wrapper approach, embedded approach, and hybrid approach. Let us talk about first approach, that is filter approach. In filter approach, feature selection is based on statistical measure. Here we'll evaluate each feature independently with the target variables. Feature with the high correlation with the target variables are selected. Means feature has some relations that can help in making the predictions or that help building a good prediction model. Okay, this approach used in pre-processing phase to remove irrelevant or redundant feature based on statistical test, that is correlation on or with the help of other criteria. So in this, we'll pass all the feature sets, we'll select best subset. If the best subset gives optimal features or optimal result, then we'll keep that features. So these are the some common technique we used in filter approach. The first one is variance, threshold, Pearson correlation coefficient, chi-square test, and information gain. Variance threshold help us to remove features with low variance. For example, in a given data set, let's suppose all the values are similar. For example, in a gender column or gender features, all the values are M. That means all the records are related to the gender male. Then this kind of a features represent very low variance, okay, or almost zero variance. So we need to remove such kind of a features from our data set. So variance threshold is a unsupervised filter based feature selection method. It removes feature with very low variance. As you can see in this table, the values, right, all the features are male except record number 4. So here we can see that 99% of the entries are male only. That means the variance of X is almost zero or 1%. So what we'll do is, with the help of this variance formula, we'll calculate the variance of feature X. If the features variance is very less, we'll reduce or will drop that column. Consider this example. In this example, let us take 5 samples. Sample 1, feature value is 10. Sample 1, feature X values are 10, 10, 10, 10. In this, first find it out the mean values. So mean is nothing but a sum of observation divided by number of observations, and we got mean value is 0. Substitute this mean values in variance formula. So the original value is 10, the mean value is 10, 10 minus 10 whole square plus 10 minus 10 whole square, and so on. So once we substitute all the values, we'll get 0 divided by 5, that is nothing but a 0. So here variance is 0. That means this feature has no variability. So this feature is not useful for building the machine learning model. So we'll remove this kind of a features from our data set. Next approach is Pearson correlations. It is basically used for redundancy removal. It is also a filter based feature selection technique where we measure linear relationship between two features, and it is used to remove highly correlated features. Okay, if the correlationship between two features is nearly like 80%, 90% or 100%, then we need to drop such kind of a feature. Why? Because the same kind of a features data is represented by some other features. So we'll remove one of two features that shows similarity or similar kind of information. So this is the correlations, Pearson correlations formula. With the help of this formula, we can find it out the correlationship between the two features, where R is equal to -1 to +1. Here +1 means perfectly positive correlation. Perfectly positive correlations. 0 means no correlation. -1 represent perfectly negative correlations. So let us take an example. In this example, feature X has 1, 2, 3, 4, whereas feature Y has 2, 4, 6, 8. As we can clearly see, the feature X and Y are almost similar. The feature X is equal to 2 times of the feature Y is equal to 2 times of feature X. So in this, let us find it out the mean values, mean of X and mean of Y. So mean of X is equal to 2.5 and mean of Y is 5. So step 2 is compute the values. So we have computed the values X minus mu X and Y minus mu X, and we'll find it out the product of these two and substitute all these values in the original formula, Pearson correlationship formula, and we got R is equal to 1. So here 1 represent these two features are perfectly correlated, perfectly positive correlated. That means the features are highly redundant. That means both the features are showing same kind of informations. So we'll remove one of the two features. So either you can remove feature 1 or feature 2, anything. Next approach is wrapper approach. It is a greedy approach where the feature selection work as a searching problem. So the wrapper approach is a feature selection method that evaluate subset of feature by training and testing a machine learning model. Okay, so in this technique, it wraps the feature selection process around a learning algorithm. So as you can see in this figure, this kind of approach is computationally very expensive, and the quality of features we can judge by accuracy of the chosen model. If the accuracy of the model is, let's suppose, like 80%, 90% or 95%, then we can say that the set of feature is a good features and we can finalize the features. These are some common techniques for forward selection technique, backward elimination technique, recursive feature elimination techniques. These are the wrapper techniques that we can use to figure out or to figure out what are the good features present in the data sets. How the wrapper approach works, let us see like how step by step this wrapper approach works. So we'll start with the initial feature subset. Either we'll start with the empty subset or full subset based on your techniques. In feature selection, forward selections, we'll start with no features. We'll start with empty subset features and add one feature at a time, and will compute the accuracy of the model and will observe the accuracy of the model. Whereas in backward elimination, we'll start with the full features or all the features and remove the least useful features or least relevant features. Step 2 is generate candidate subset. So we can add or remove features. And the third step is to train a model using each subset, evaluate the performance and best performing subset we can keep it, and at last we stop the process when improvement is minimal or stopping criteria is met. These are the techniques: feature forward selection, forward selections, sequential forward selections, sequential backward selections, and recursive feature elimination techniques. So in this forward selections, start with no features, add one feature at a time, whereas in sequential backward selection we'll start with all the features and will remove the least useful one. And in recursive feature elimination techniques, repeatedly train the model and remove the least important feature based on model coefficient or feature importance. The common models we can use in these techniques are linear regression, SVM, or random forest in order to find it out the coefficient or feature importance. So this is one example of forward selection approach. Consider this data set. In this data set, we have 4 features. Feature 1, study hours. Feature 2, attendance. Feature 3, mobile usage. And feature 4, sleeping hours. And the target column is pass or fail. So in this method, forward selection method, we'll test each single feature. Okay, so at starting, we'll find it out the accuracy of the model on only feature 1, on only feature 2, on only feature 3, or only feature 4, and from there we can select a feature that give maximum accuracy. So in this we can clearly see the feature 1 gives accuracy 70%, that is highest among these 4. So we'll select the feature 1 and add it in our subset, and the next step is add remaining features one by one. Okay, so so in this step we'll combine F1 with F2, F1 with F3, F1 and F4, and again we'll evaluate the performance of the model. So as you can see, F1 plus F2 gives 78% of the accuracy, F1 and F3 gives 72%, whereas F1 and F4 gives 75% of the accuracy. So we'll select feature 2. Why? Because along with feature 1 and feature 2 gives better accuracy compared to F1 and F3 and F1 and F4. So we'll select F1 also, and the next step is we'll keep on adding the features. Okay, and when there is no improvement, we'll stop the process. So in this hypothetically we can say that the feature 1 and feature 2 are selected based on these performance matrices. In the same way, backward selections will train the model with all the features and we got accuracy 85%, and in step number 2 we'll remove one feature at a time. We'll find it out which features, by removing which features our performance drop is least. Okay, so as you can see here, if I remove feature F3, our performance drop by only 1%, then we can say that these are the subset of feature in this stage, F1, F2 and F4. Again we'll repeat the same process and we'll observe the accuracy. In the next stage also we can say that by removing F4, our accuracy is similar to the previous one, so we can say that our F1 and F2 is the best feature that give the accuracy 83%. In recursive feature elimination techniques, we'll train the model using all features. We'll compute the feature importance based on some techniques like linear regression, SVM, or a decision tree, and we'll find it out the coefficient or Gini importance, and we'll rank the feature from most to least important and we'll remove least important features and retrain the model with the remaining features, and we'll repeat this step like k times until we'll meet the stopping conditions. So as you can see here, in iteration 1 all features are considered, and all features are considered individually, and f1 coefficient is 0.82, f2 coefficient is 0.61, f3 coefficient is 0.15, f4 coefficient is 0.32. Among these, the lowest importance is feature 3. So what we can do, we can remove f3. Why? Because it's so very low importance in the training of model. So in the same way, we'll do the feature selections for remaining features also, and at last we'll select f1 and f2 based on the coefficient. These are the some commonly used model with recursive. These are the commonly used model with recursive feature eliminations. The model name is linear regressions, logistic regression, linear SVM, decision tree, random forest. So these are the important measures, techniques. So for linear regression model, we'll find it out the coefficient, whereas for decision tree, we'll find it out Gini or entropy. So advantage of RFE is we'll consider feature interactions, okay, and it produces compact and high performance feature set widely used in research and competitions. Disadvantages is computationally it is very expensive, not suitable for large feature sets, and the risk of overfitting is very high in such kind of approaches. So another technique is embedded approach. In this approach, the feature selection technique, where feature selection happened during training, model training itself. So here the model automatically select important feature while learning instead of doing as a separate step. Why it is called as embedded? Why? Because feature selection is embedded inside the learning algorithm. No separate feature evaluation step is required, and the selection is guided by the model objective functions. So these are the some techniques that we can use in embedded approach. The first technique is L1 regularization, decision tree and random forest, gradient boosting. These are the comparison of various approach: filter method, wrapper method, embedded method. This filter method much faster compared to wrapper method in terms of time complexity, whereas wrapper method take more computation time for dataset with many features, whereas embedded method is basically balanced between these two. This is the code. With the help of this code, what we can do, we can find it out the important feature and we can rank the features. So here this RFE is wrapped with the logistic regressions. With the help of RFE method along with the logistic regression, we have selected some features and we rank them in a particular order in order to select the best features. The next important concept is feature scaling, the magnitude problem. As we already know, the data we get it from various sources, and once we perform the cleaning and feature selection, the next important point is feature scaling. Consider this scenario. This model predicting health score, the ages, let's suppose, is ranging from 0 to 100 and steps per day is 0 to 2000. The problem in this kind of a data set is the algorithm assumes steps per day is 200 more important than the age because of the magnitude. So the solution is normalize the data. So why normalization is required? Why? Because some of the technique or some of the algorithms is based on the distance measures. For example, KNN and support vector machine rely on the distance calculations to measure the similarity between the data points. That the core problem here is the dominance, scale dominance. Feature 1 ranging from 0 to 10,000, let's suppose, feature 2 ranging from 0 to 1. Even a small change in feature X produce much larger square term than the feature Y. As a result, feature X dominate the distance computations, feature Y become almost irrelevant. That's why feature scaling is required. And also this feature scaling impact on the gradient descent efficiency. Uh, in terms of optimizations, this unscaled features make the cost functions elliptical, and during the gradient descent process, the process oscillate between the step and flat directions, and that basically result in a slower convergence, more iteration, and possible failure to reach the global minimum values. If the data are scaled, then we can say that the data or feature are on a similar numerical scale. The cost function become more circular, and gradient points directly toward the minimum. So the normalization ensures that the feature contribute fairly to distance calculation and optimizations, leading to fast convergence and better model performance. These are the some techniques with the help of that we can perform normalization. The first technique is min-max scaling, where we can is restrict the data between 0 to 1. The second technique is standardizations, where we'll try to keep the mean as 0 and standard deviation as 1. It is handles outlier more better than the min-max normalizations. So selection versus scaling. So the question is, do I scale before or after selection? The answer is we can first perform the selection process and then scale down the data for model building. So the summary of this lecture is, during feature engineering, first we'll draw feature with the low variances, select features using filter, wrapper or embedded techniques, scale the feature if using distance or gradients based model, and evaluate the performance of the model at each step to build a better machine learning model. Thank you.